Now let's do an example with this configurable adder. So as we said, we can configure it to be a full adder or a subtractor. So let's see how it is working and make sure it is working correctly. So let's say I have a variable a 0 1 1 0 and variable b 0 0 1 0. So let's see, if we do an addition, what we will be getting is 0 0 0 1 0, right? So this is our sum. So let's see in the circuit it is working, right? Since we are doing an addition, our m variable is 0. So what we will be putting, we will be putting a 0 input here, a 0 here, 0 here, 0 here, 0 here, right? And our b0 is 0, so b0 is 0, b1 is 1, b2 is 0, and b3 is 0, and a0 is 0, a1 is 1, a2 is 1, and a3 is 0. So let's do the addition. So before we do the addition, we need to do this XOR operation. 0 XOR 0, I have a 0 here, and 0 0 0, my sum is 0 here, my carry is 0 here. So this is 0, I have a 1 here, 0 and 1 XOR operation, I have a 1 here, 1 and 1, and 0, I will get S1 is 0 and my carry out is 1, so I will get a 1 here. So 0 XOR 0, I have a 0 here, 0 1 1, right? So I will get a S2 will be 0, but my carry out will be 1, so this is 1. So 0 XOR 0 0 0 0 1, so S3 is 1, carry out is 0. So my result is 0 1 0 0 0. So this is actually the same as what we expected. So this is working for the addition. So let's do the same example with the subtract operation, right? So in this case my m will be 1, and then I will be doing a subtraction. Let's do the subtraction. 0 minus 0, I have a 0, 1 minus 1, I have a 0, and 1 minus 0, I have a 1, and I have a 0. So this is my result of subtraction. So let's do this subtraction. So I have a 0 here for b0 and 1 for m. So XOR operation is 1. So this is 1, 0 and 1. So the sum should be 0. My carry out is 1. So I have a 1 here. A1 is 1, B1 is 1, and M is 1. So 1 and 1, I got 0 here. 0 1 1, I got 0 here, and 1 at the carry out. So I have a 1 here. So my M is 1, 0 and 1, I have a 1 here. I have 1 1 1. So my sum is 1, my carry out is 1. So M is 1 here, 0 1, I have a 1 here, 1 0 1. So I have a 0 here, but the carry out will be 1. So since I am using only 4 bits here, so this result is the same as this one, right? The result, and I will be discarding this carry out. So in this case, if m is 1, we did the subtraction and we verified our result is the same as our expected results if we do by hand. Okay, now let's design a BCD to XS3 converter. Example, design a BCD to XS3 converter. So the first method, we should do it using the truth table, and the second part we should do this using a 4-bit adder. As you will remember, in BCD we were representing the digits, decimal digits. So this is our BCD code, and in XS3 all we need to do is add 3 to this, right? So this is 3, this is 4. So this is XS3. So we need to do this conversion, right? So in a way I have 4 inputs and this is my outputs, right? I have 4 outputs. So this is BCD. Let's call this A3, A2, A1, A0. And for the XS3 we will have, let's say, as an output E3, E2, E1 and E0. So I have 4 outputs. If I use the truth table method, I need to make a Carnot map for each of my outputs. So let's say A3, and then I draw my 4 variable Carnot map. So this will be A3, A2, A1 and A0. So, and I need to find out where our ones is. So this is my ones, right? So I have a 1 at this location, 0 1 0 1. So this is 1, 0 1 1 0. So this is another one, 0 1 1 1. So this is another one, 1 0 0 0. So this is 1, 1 0 0 1. So this is 1. So for 10 to 15, I have a don't care, right? I have a don't care for this one, which is x, 10, 11, right? 12, 13, 14, and 15, right? So this is 15, this is 14, 13, and 12, right? So where is 10? 1 0 1 0, 10 and 11. So these are my don't cares. Now I need to find the function for E3. So what is E3? So I need to cover all these ones. Actually, I can make a group of 8 here. So this is one group, and this is represented by A3, right? So this is A3. So I will say E3 is A3, or then I need to cover this group. I can cover this group. So this group is A2 and A1, right? And then another group is here. So this is another group of 4. So this is A2 and A0. So then the result is A1, A2, or A0, A2. So this is one function. Similarly, I will do the same thing for E2. I do the Carnot map. I will do the same thing for E1 and E0. So at the end, I will get a Boolean function for each of them. And then I will implement this using the gates, right? For E3, I will get, for example, this will be A1, A2, another AND gate, A0, A2, and then I have this A3, and then I will have an OR gate. So this will be my E3. Similarly, I will be doing other gates for A2, A1, and A0. But I will leave it to you to do all these operations. And then I will be doing the same thing using a 4-bit adder, right? All we need to do, if you look at the inputs, so I can say A3, A2, A1, A0. And I am adding 3 to this, and I will be getting A3, A2, A1, and A0. So how can I implement this? So I can implement this using 4-bit parallel adder, right? So this is my full adder. So this is my E0, this is my E1, this is my E2, and this is my E3. So I have A0 here, A1 here, A2 here, A3 here, and I have a 1 here, 1 here, 0 here, 0 here. And this is the implementation of BCD to XS3 converters using the full adder, right? But if we use the Carnot map approach with the truth table, we have to draw 4 Carnot map and then simplify each of them, then implement it. So, but both will be doing the same thing. One is easier for us to do than the other. So the second part was faster. So let's do another example with the adders. In this example, we will design a circuit that computes the average of two 4-bit unsigned numbers. If the average is not a whole number, for example, if it is 2.5, then you must round down the result. So you must round down 2.5 to 2.0. So to find the average, we need to add these two numbers, and then we should divide the result by 2, right? So this is actually what we need to do. Assume we have variable x 3 to 0 and y 3 to 0. So this is a circuit that we need to implement, and then result is average 3 to 0. So what should we have in this block? So what we can do, we can make a 4-bit adder, right? Let's say again we can draw our 4-bit adder. So this is my x3, y3, x2, y2, x1, y1, x0, y0, right? So the result will be, this is S0, S1, S2, and S3. So this is my sum. So I added these two numbers. To take the average, then I need to divide by 2, right? So I need to divide the result, the sum, by 2 to get the average, right? So how do I divide by 2? So dividing by 2 means shift one position to the right. So this is my result S3, S2, S1 and S0. So I will be connecting this to average 0 and I will be connecting this to average 1 and to this average 2, right? Then my average 3 will be 0 to this one. So then we will be getting this circuit that computes the average of the two 4-bit unsigned number, right? So let's see if it is working. Let's make up some numbers. Let's say my x is 0, 1, 0, 1. So this is 5 and let's make y is 2. So I have 0, 1, 0, 0 for y and 0, 1, 0, 1 for the x. So if I do this addition, of course, in this case, we can always connect this carry into 0. So what will I get here? I will get 1 here and 0 here. So I will get another 1 here, right? And 0 here, another 1 here and 0 here, right? So then my average number will become, so I have a 1 here, another 1 here and 0 here, 0 here. So what is this? So this is my average is 3. I added 5 and 2. Result is 7. If I divide it by 2, 3.5, but I need to round it down to 3.0. So for this example, it is working, right? So now I got my average to be 3. We can try another example. So let's say I got 1, 1, 0, 0 here. So this is 12, right? And let's add it with 4, right? So I should be getting a 5-bit 16. But if I divide it by 2, then I will be getting 8, right? So let's see if it is working because now it is going up to 5 bits. So let's put our numbers. So I have 1, 1, 0, 0 here and 0, 0, 1, 0 here. So I got 0 here. I got 0 here, another 0 here, 0 here. I got 0 here, 1 here, 0 here, and 1 here, right? So in this case, average 0 is 0, S2 is 0, S3 is 0, but average 3 actually instead of putting it 0, I should be getting a 1 here, right? I should be connecting my carry out to my average 3. So now I will be getting 1 here. It will be the same, right? So in this case, since we have a carry out, in order for my circuit to work, I need to connect my carry out to average 3. When I shift it, I will be getting the same number. So this was the calculation of the average of the two unsigned numbers. Okay. So you can also try other numbers and then you can see whether it is working or not.